Well, we're going to explore some exciting challenges to astronomy. That's why I'm calling this Beyond Newton. We're going to discover that Sir Isaac Newton has had a profound influence on the astronomers, but they haven't looked beyond that in some sense. Now, this is the fourth of a series of 3. That may sound funny, but about 16 years ago, we published a series of studies. One was called Beyond Time and Space, which we've just republished afresh. And it primarily dealt with the impact of Einstein's theory of relativity and our understanding of the Bible. We talked about the nature of time, the nature of space and hyperspaces, and the challenge of nonlinearities all around us. That was all taken up in that first publication, which we've recently republished and freshened up. A second member of the trilogy was Beyond Coincidence, evidence of deliberate design in the universe and in the Word of God. We talked about the anthropic principle, the apparent reality that the universe seems to be designed for man. And we also talked about hidden messages in plain sight. All that was in Beyond Coincidence. And we explored statistically, how sure can we be of these things? We glibly talk about the Bible being the Word of God. That sounds great. How sure can we be? And we dealt with that in empirical terms. And then the third of the trilogy was Beyond Perception. And this was an exploration of the nature of matter, the subatomic world, and how it appears that we may be in a holographic universe. We're going to discover, and also we explored dimensions beyond our own. So one of the things you should recognize that we're going to borrow on some parts of all of these for this fourth member that we're going to add. We had this trilogy, we're adding a fourth member to it, and there will be a little bit of duplication here. You'll see why. I'm calling this fourth addition to our traditional trilogy Beyond Newton. And we're going to challenge here the myths of astronomy. And it really shocked me to realize how much of what we think we know about astronomy ain't necessarily so. And so I'm also going to throw in a little addenda in here I'm going to call Epistemology 101. What do I mean by that? I'll explain when we get there. We'll talk a little bit about the scientific myths of the past and of the present. And we'll talk about the milestones of influence that have occurred to bring us to this point. And we're going to show you a celestial model called the Burnham model. It's a standard model, but the implications of it may surprise you. And so we're going to lead then, of course, to the discovery, at least for us, of what some people call the plasma universe. So let's take this little preamble I'm going to call Epistemology 101. Epistemology is just a fancy word for the study of knowledge, its origin, its scope, and its limits of knowledge itself. And if you take this in college, it's a waste of time because it's administered by the Department of Philosophy, and it just becomes a study of the use of words through history. They don't talk about resources or tools as you'd expect them to. And I'll have to start with this little quote from Look Through the Looking Glass. Alice says, "One can't believe impossible things," she laughed. "I dare say you haven't had much practice," said the Queen. "When I was your age, I always did it for a half an hour a day. Why, sometimes I believed as many as 6 impossible things before breakfast." And of course, that's Lewis Carroll with his tongue in his cheek, pointing out something that we all are guilty of, believing impossible things. So I want to talk a little bit about the myths of the past. We believe that there were many ancient cultures that believed the earth was flat. And they should know better because your Bible tells you several places, Isaiah 40:22, that the earth is a circle, a sphere. And another thing that came along in the 17th century was the idea of phlogiston, which is a material that caused things to burn. That was the way they thought things burned, because they had this peculiar material in it. And obviously they learned that it's actually oxidation, and the whole concept of burning was in error for a long, long time. It's a classic example. We all probably know about the Ptolemaic cosmology. The idea in the days of Ptolemy, they thought that Earth was the center of the universe, that the sun rose in the morning, set in its side. They actually had what's called a geocentric concept here. And that, of course, was replaced by what we call the Copernican cosmology, where the sun is the center of our solar system. Not of the whole universe, but of our solar system. Ptolemy, of course, in Alexandria, he is going to go down in history as opposing two fundamental truths in science. He, of course, was wrong about having a Earth-centered solar system. We know we have a sun-centered solar system. He also argued it was impossible to have four dimensions, interestingly enough. He proved that a fourth dimension was impossible because he couldn't visualize a fourth thing perpendicular to the other three. You think of one line, the idea of orthogonal or perpendicular, he said it was impossible to have four, and of course he's wrong, and he's going to go down in history as being wrong on both of his main points here. Higher geometry, in fact, is the key to understanding other conceptions of our universe. We covered that in one of our previous sessions. But another myth for a long time, they looked for ether. Ether was the medium by which light can travel through the universe. How can light travel from here to the moon? Must be something in there for it to travel in. They call that ether, look for it, and so forth. But the Michelson-Morley experiment back in 1887, which incidentally occurred on the Naval Academy grounds, by the way, proved that ether didn't exist. They tried to measure it, didn't exist, so that punctured a common myth of the time. The velocity of light is another one, and it was interesting that it was under Descartes and so forth, they thought light was, the speed of it was infinite, or putting another word, light was instantaneous. And but an astronomer by the name of Romer, Olaf Romer, found a way to measure the speed of light by watching the eclipse of a moon on Saturn, and so he measured it, the speed of light, that it was very fast but finite. And it wasn't for 50 years later that Bradley, an Englishman, did the same thing, and they finally accepted that light had a specific speed. The interesting thing here, aside from the physics of light, is to realize even the physicists, it took them 50 years to swallow the meaning of empirical data. That we can constantly create theories that are not quite correct and cling to them in the face of experimental data to the contrary. When you find something that doesn't agree with your theory, you find an excuse to throw it out. No, we should be listening to it. And we always thought that light was a constant. Satterfield-Norman has discovered it's not a constant. We'll talk a little bit more about that in our next session. This velocity of light, see, in the 17th century, Kepler and Descartes, they thought it was instantaneous. But it was Olaf Romer in 1677 that looking at the eclipses of Jupiter with its two moons yielding a finite speed of light. And it was 1729 that Bradley confirmed that, but it took 50 years for acceptance. And so, well, let's talk about the myths of today. These, we look back at the laugh and we smile at the people, they had these wrong answers. Today we have evolution, which is provably not true. And that when I say evolution here, what I really mean is biogenesis, but everybody calls it evolution. Michael Denton, Philip Johnson, Michael Behe, these authors have written books in recent years that destroy, that demonstrate that evolution no longer is a viable explanation for what we know about the universe. And yet, it's still taught in schools, our whole society presume it's a myth that everybody accepts. It's contrary to fact. The velocity of light is a basic constant. And of course, Satterfield-Norman, that many people still believe that, by the way, many physicists do, but it's been statistically confirmed that it's been slowing down. We're going to talk a little bit more about that in the next session. Well, I want to talk about another one that's more at home to some of the things we're going to talk about here today, and that's the thing called the nebular hypothesis. Where did the planets come from? And Immanuel Kant and Laplace embraced this idea, and we want to talk a little bit about that. And it goes something like this. And Immanuel Kant wrote in his General History of Nature and the Theory of Heavens, he says, some 4 billion years ago, the sun had ejected a tail or a filament of material that cooled and collected and thus formed the planets. So it goes. Now, these ideas are still taught in college courses today. Understand that. 21 years before Kant said that, a guy by the name of Emanuel Swedenborg, that's where the idea came from, that he wrote it in Latin, but it became, he was a mining engineer with a lot of interests, and he claimed to have psychic powers. And he claimed that he learned this from seances with men on Jupiter, Saturn, and other places. In other words, he was a mystic in the negative sense, but he came up with this idea. When Swedenborg was 24 years old, he had an opportunity to meet Edmund Halley of Cambridge, who was famous for the comet and all of that. And so he had some astronomy background, and he came up with this idea that's where the planets came from. And Kant picked it up and published and sanctified it by giving his credibility to it without check, and then so did Laplace, and Laplace should have known better. Pierre Laplace he lent his endorsement to Kant's theory without checking the math, and he was capable of doing that but failed to do so. So then this nebular hypothesis gained widespread respectability despite the fact that it includes very serious mathematical errors. And subsequent writers have continued to develop variations of this view, even though increasing difficulties make it highly unlikely, and yet it's still taught today. The sun contains, it turns out, about 99.8, say almost all of the mass of the solar system. We're talking about the planets, the sun and the planets. Almost 100% of the mass is of the sun. It's gigantic in comparison. Yet the sun contains only less than 2% of the angular momentum. That's a strange thing. The angular momentum is all concentrated in the planets. The 9 planets contain 98% of the angular momentum. There's no way to explain how that happened. It's there. You can measure it. It's real. What causes it to be, it turns out there's no way to explain how that happened. All this was known in the time of Laplace 100 years ago. But he didn't think it through. That's why the nebular hypothesis doesn't make sense. There's no plausible explanation that would support a solar origin of the planets. But it gets worse. James Jeans, that's in the from 1877 on, pointed out that the outer planets are larger than the inner ones. Jupiter is almost 6,000 times as massive as Mercury. It's almost 3,000 times as massive as Mars. And so that's hard to explain. It goes against the concept here. And so this is a difficulty with all current theories. I'm going to show you before we're through, there's some theories that explain this, but we'll move on. Some other enigmas. There are 3 pairs of rapid spinning rates among our planets, each within 3% of others. In other words, the planets there's in pairs in which they're almost the same numbers. And so the Earth and Mars, Jupiter and Saturn, and Neptune and Uranus, they're all within 3% of each other in terms of the way they spin. Earth and Mars have virtually the identical spin axis, about 23.5 degrees. That's what gives us our seasons, spring, summer, and so forth. Why? Why do these planets, why are they in pairs? Nobody knows. From angular momentum and orbital calculations, it would seem that 3 pairs of these planets may have been brought here from elsewhere. They somehow came out of some phenomenon yet undisturbed. Why does Mars have 93% of its craters on one hemisphere and only 7% on the other? It would appear that over 80% occurred within a single half hour. Why? See? Well, the planet Mars, of course, is a mystery anyway. It's the 4th major planet from the sun. It's named after the Roman god of war, Mars. We still use that term, martial arts, and so forth. Most of the early civilizations were terrified of that planet. Why? It was the Baal of the Old Testament, incidentally. Why? Well, first, what we discover when you get into this, you'll discover that scientists fall into 2 categories. Most of them are what we'd call uniformitarians. They mean they cling to the idea that things have remained essentially unchanged over billions of years. That's one philosophy. There are others that are called catastrophists. They believe that the universe has been subjected to a series of catastrophic events. That's what gives you all these. Look at the moon through a pair of binoculars. It's been beat up. And as we send probes to the other planets, we see the same thing. There's craters. The solar system is a rough neighborhood. And the fiat creationists, by the way, those of us that believe the Bible, would be in the second category. That would be categorized as a catastrophe. God intervened to make these things happen. The uniformity delusions are, view any surface in the solar system, there's craters and disruptive influences. Under a constant rain of interplanetary debris, the Earth itself still collects about 100 tons of extraterrestrial material per day. Many people don't realize that. There are over 100 craters on the Earth that by erosion and so forth, they're not as conspicuous. There are asteroid impacts all through history. Tunguska in central Siberia in June 30 of 1908 is a very famous one. It destroyed over 2,000 square miles of forest, or kilometers of forest. It was so remote that it wasn't explored for 17 years later. It's really a remote place. The damage there is equivalent in megaton, in nuclear terms, of like a 15 megaton equivalent. There's a meteor crater near Winslow, Arizona. It's a mile across, often visited. And they've discovered a big one on the Yucatan Peninsula at about 6 miles in diameter, 100 megaton equivalent. Apparently, it's about every 300 years we have one hit the Earth, and there's 1 in 3 of these are on land. The other 2 are, of course, in the ocean, so you don't see signs of it. Well, see, the ancients were sensitive to this, apparently. There was a meteorite that created the whole, that ends up creating the Kaaba in Mecca that they still worship, a meteorite stone that's in there. 2,000 years before Muhammad. That wasn't invented, that's something Islam adopted. It was there thousands of years before. The word Cairo, the city of Cairo, was named, that's Arabic for the planet Mars. Why? What's that got to do with pyramids and all of that? And of course, that's the site of the Great Pyramid and so on. Athens, we all speak of the Areopagus in Acts 17. Ares is the name in Greek for Mars. It's pictured as a source of judgment, really. Yeah, Mars Hill, that's why they call it Mars Hill, and the Areopagus in Greek. And Dionysus was a member of that sect. Well, in the Bible, of course, we encounter a strange event called the Battle of Beth Horon in Joshua chapter 10. The kings there confederate against Adonai-Zedek, the king of Jerusalem. He's sort of a foreshadowing of what we call today the Antichrist. He's defeated with stones of fire from heaven. And the sun was commanded to stand still, be silent, to give Joshua more time to complete the route. And the sun and the moon were extended apparently for the equivalence of a whole day. And kings hide in caves and are dealt with, and that completes the whole southern strategy of Joshua's thing, and the rest of the book of Joshua is just a cleanup after that. Well, what is this business of Joshua asking the sun to stand still? Most of us think, well, gee, that would mean the earth would have to stop spinning. No, it turns out all you'd have to do is change the precession a little bit. It would accomplish the same thing. But it's interesting, we discover that all ancient calendars were based on 360-day years. And typically 12 30-day months making a year. But then they change. In 701 BC, all these ancient calendars have adjustments made to them. We discover that Mars was worshipped by the ancient cultures. And out of all of this background, there is a hypothesis that is hard to disprove, that Mars made near pass-bys to the Earth. I'll come to that in a minute. But the idea is that Earth and Mars originally were on resonant orbits. Resonance, the orbits act just like tuning forks. If you have a tuning fork that you hit and there's one of the same frequency across the room, it'll resonate to it. Orbits are the same way. Orbits will have a tendency to get in step with either the primary or the harmonic of its rotation. Well, the Earth and Mars apparently are believed to be originally on resonant orbits. I'll show you a diagram here in a minute. And they had near pass-bys every 108 years. And it turns out by modeling this, it would account for catastrophic events on a number, in fact 7 of them, throughout recorded history. And these energy transfers all apparently stabilized in 701 BC, which caused the calendars to be redone. And so let's take a look at this. You have the Earth. We know that the Earth is at the foci of an ellipse, and like all of them are. And it's not necessarily a circular, it's an oval, but we're at the foci of the oval. And Mars is the same thing, except they overlap. And originally, they were on resonant orbits. The Earth on a 360-day orbit, Mars on a 720-day orbit. But there were times when they came near each other every 108 years. In the spring, if they came near each other in the spring, it would be March 20th, 21st. It would be inside after perihelion, and Mars would lose a little energy, Earth would gain a little energy. They'd pass again every 108 years, but the next one would be in the fall, October 25th, and it would be, this time it would pass behind the Earth, and there would be the Earth would lose a little energy, Mars would gain a little energy. This kept going on until it finally stabilized And that's when the 360-day orbit becomes 365 and a quarter. That's why we have a leap year and some months different. And that's at Mars, it went from 720 down to 687. Earth gained a little, Mars lost a little. Now, that's a theory, but it turns out there's a tremendous amount of support for that. But one of the most provocative confirmations comes from all places from the travels of Lemuel Gulliver, which is a children's story written by, as we would look at it, by Jonathan Swift. It actually was some political satire of the day. We regard it as some children's stories. But before we get into that, I want to review telescope technology. Most of you know that Galileo was famous for the first serious use of the telescope in 1610, and with that he discovered the 4 moons of Jupiter and Saturn's rings. Big deal. 1781, Herschel, with a better telescope, discovers the planet Uranus. A little later, a couple of years later, in fact, 6 years later, he discovers the 2 moons of Uranus. And then a couple of years later, he discovers 2 more moons. See, the telescope technology is improving, better telescopes. Till you get to 1846, Leverrier discovered Neptune and one of its moons. Then you get to 1877, a guy by the name of Asaph Hall, with a brand new telescope in the United States Naval Observatory, he makes astronomical history because he discovers that Mars has 2 moons. They didn't know that. And he names them Deimos and Phobos. And Deimos has an orbit about 30 hours and 18 minutes. See, our moon has a 30-day orbit, right? This one has a 30-hour, it's 18 minutes. And it's almost synchronous. In other words, it would appear almost to be stationary. And then Phobos is 7 hours and 39 minutes. And Phobos is unique in the entire solar system. It's the only one that goes backwards. Everything else goes westward. This one particular satellite, for some reason, is going eastward. And the reason it's so hard to see, it's very small. It's only 8 miles across. And it is almost black. It has a reflectivity of only 3%. In other words, it's almost black. That's why it's so hard to see. That's why it made such history when Asaph Hall spotted it. Little background. Well, that's 1877. Jonathan Swift published his story called Gulliver's Travels. It actually was a collection of essays for political satire, but in 1726. Now, we all know the Gulliver who visited the place called Laputa with all the little people, right? That's our story. The third voyage of Gulliver, different story, but in the same collection, is he goes to a place called Laputa. And in Laputa, the astronomers there are they make fun of London because they know about the 2 moons of Mars and the people in London don't know about it. It's just in the story, just a colorful children's story, except in the story, it details the size and the revolutions of these 2 moons of Mars within about 20% of what we know of them today, and it mentions that one of them is going backwards. Now, the problem is, how did Jonathan Swift put that in the story? Because he published that 151 years before the astronomical world discovered the 2 moons of Mars. Well, we don't know. We presume that what Jonathan Swift did was that he drew upon some legends to embroider his little story. He probably didn't realize that what the legends that he was drawing upon were actually eyewitness accounts. They'd have to be eyewitness accounts because this 151 years before he had the telescope technology to see these things, unless Mars got so close on one of these pass-bys that you could see them with the naked eye. That's why this is such a provocative piece of news. Now let's talk about the long day of Joshua. 1/3 men were at Beth Horon. And October 25th, 1404 BC, Mars was on a polar pass at 70,000 miles. That's very close. And appeared to rise 50 times the size of the moon. Severe earthquakes and land tides. Polar shift of about 5 degrees would lengthen the day, incidentally. Meteors followed about 2 or 3 hours later at about 30,000 miles an hour. And this whole drama is included in other ancient legends and folklore also. There's we're indebted to Emanuel Velikovsky, who discovered there's a legend of a long night in China in this period. So all this seems to be corroborative of what the Bible is. It sounds so strange to us, but we discover when you get behind the scenes, it's not so strange. Well, let's get back to modern physics. Under Einstein, of course, we know that we have a four-dimensional space-time. We consider it curved by the presence of matter, producing a universe whose geometry is Riemannian rather than Euclidean, and we covered all that in one of these previous things. I don't want to go through it all again, but I want to tie it to some of the things we've done before here. And the whole idea that bodies that travel in geodesics, that shortest paths, are curved orbits interpreted by Newton as a result of some attractive force. And then we have the scientists looking for gravity waves. We're spending a lot of money on GEO 600 looking for things called gravitons. And we covered that last time in the beyond perception thing in terms of looking for these particles. We've never seen them, but they assume they exist to account for gravity. And these are massless, uncharged particles moving at the speed of light, presumably, but so far they're undetected. These are fabrications of imagination to try to repair some theories. And the GEO 600 experiment, which they're looking for the gravitons, they've discovered, more interestingly, evidence that we may have a holographic universe. We've talked about that before, but I want to get this in perspective. So I want to get into this epistemology 101 issue. I want to talk about the scientific method. We use that phrase all the time. What we really mean is the empirical method. How does it work? The concept of the scientific method is, number one, you observe a phenomenon. You see something and you measure it and take recordings. Then what you do is you seek patterns and measures of your observations. That's all gathering, data, in other words. Then you formulate a hypothesis, a conjecture, if you will, from that description, and then what you try to do is you gather independent data to challenge the hypothesis. That's what we mean by the scientific method. Now, it may shock you to realize that your whole process is to search for failures. You've got this hypothesis, you want to try to disprove it. If you can't disprove it, that reinforces the credibility of your hypothesis. Theories can never be proved. That may shock you. They never can be proved. What they can do is they might defy being disproved. Someone has a theory, great. You try to disprove it. If you can't, that starts to elevate that hypothesis to the level of a theory, but it may get more and more credible the more you try to disprove it. But it's never really proven. That's an important concept to get across. Now, Shannon, we're now in the area of what we call the information sciences. Claude Shannon defined what he called the verifiability definition of meaning. What do we mean by meaning? It has to be verifiable to have meaning. Untestable statements are meaningless. Grandma says there are gnomes in the garden, but they always manage to be invisible when you're looking for them, you see. Well, we smile at that, but the point is, you see, that's a meaningless statement. Why is it? Because there's no way to verify it, you see. Well, you can't disprove it. That's not proving it's true. So untestable statements are meaningless, according to the Shannon verifiability theory of meaning. Huxley said, the great tragedy of science is the slaying of a beautiful hypothesis by an ugly fact. You see, facts that aren't convenient for your theory, often people try to discard them. Well, find some excuse why that doesn't fit the theory. Well, that's not being scientific. Non-falsifiable hypotheses are not only non-scientific, they're intellectually dishonest. The idea of a hypothesis, it should be testable. And if you can test it and can't disprove it, that doesn't prove it's true, but it gives it a step in that direction. In logic, they have a thing called argumentum ignorantium, the argument from ignorance. The assertion that something must be true simply because it hasn't been proved false is nonsense. And yet we'll find ourselves, if you're not on your guard, we do that all the time. Because you can't disprove it, it must be true. No, no, no. Error, error, error. So if you can't use scientific method, and many people can't, people that are dealing with cosmology, what happened 100 billion years ago, we don't know. In other words, you make guesses, and remember that they're guesses, fine. What are substitutes for the scientific method? Well, one is called the deductive method. You derive theories from generalizations about the universe. Somebody has a generalization that seems acceptable, and we derive theories from that. That's not the same thing as proving they're true. You follow me? They're deductively logical, yeah. Here is the big one. what we call mathematical proofs. People make very elegant consistencies within a synthetic universe, a man-made. Mathematics is sometimes called the man-made universe. You define some symbols, and you define how they relate to each other, and you find that that relationship or that model is useful. And so you start getting into that more and more elegant models. The thing you lose sight of is you want to have evidence that that model fits reality. Many times it'll fit reality for a certain domain, but not others. And examples are, there are rules that occur in physics of the kitchen that don't fit in the area of the atom. The equations are different because there's different forces at work and so forth. The point is we can make very, very elegant models mathematically, but they are not reality, no matter how elegant they are. And one of the things we're discovering is that some of the most brilliant minds on the planet Earth are deeply involved in the most elegant mathematics you can imagine. That doesn't mean they fit reality. And that's what we're going to discover. Much of the theories about the so-called Big Bang, these things that come out of astronomy and astrophysics, are being end run by ugly data. Doesn't fit the model. There's another thing called domains of validity. I've touched on that. There's a model or a set of equations that may have a limited domain of validity. And that's why it needs to be tested. They have carbon-14 for dating, but it turns out for long dating, there's errors that creep in. So you always need to validate the model you're using. But the other thing that's taken place in the scientific world, in the absence of those things, are what we call peer review. In other words, you've got a scientific theory, you submit it to a publication, and you have other scientists that are considered your peers react to that and to give it encouragement or discouragement, if you will. It turns out that's the way our world really works. Publish or perish is the idea in universities. You need to publish that in a peer-reviewed journal and get their reactions. If they like it, you're elevated. If they don't, you're rejected. You're a victim of the peer review. Well, that just ossifies or freezes the current assumptions. And it really results in the censorship of competing hypotheses. If the people reviewing your paper hold theories that are different than yours, they're likely to disparage that. And that's not just in theology, it's even in physics. That may surprise you. So some caveats. Inference is not proof. You can make an inference, but that's not the same as proof. Something else, to give you another example, you want to avoid the logical fallacy of asserting the consequent. Let me give you an example. If A, then B. In other words, if B is true, therefore A is true. That makes sense, doesn't it? Not necessarily. The street is wet, therefore it must be raining. No, this ignores a possible alternative issue. A street cleaning machine just went by. See, just because if A then B doesn't, and you happen to know B is true, doesn't mean A is. Because we could give other examples, but that's the idea. The illusion of knowledge. The only one certain barrier to truth is the conviction that you already have it. And that pervades in most people in professional fields because they believe they've got a truth, and that makes them blind to competing truths, if you will. And Borson's saying, the greatest obstacle to discovery is not ignorance. It is the illusion of knowledge. The Lord has haunted me with this phrase for many, many months, and now I'm beginning to understand what He's leading me to. Metaphors reign where mysteries reside. How often there's something we don't understand, we give it an elegant name or an anecdotal relation, and that takes over instead of analyzing the mystery. Metaphors reign where mysteries reside. Science versus we say science and technology. Great. What's the difference between science and technology? Technology produces useful products. That's why we have cell phones. That's why we have computers. That's why you can make a long list of the incredible things that have come to us in the last 30, 40 years. The changes are astonishing from technology, because technology is validated by having things happen. Okay? Science has become a religion with a priesthood. I've used this before, but I loved it. It just fits here. It's a little poem I saw as a kid. I find it fits physics so perfectly. The Blind Men and the Elephant. It was 6 men of Hindustan, to learning much inclined, who went to see the elephant, though all of them were blind, that each by observation might satisfy his mind. The first approached the elephant, and happening to fall against his broad and sturdy side, at once began to bawl, "God bless me, but the elephant is nothing but a wall." The second, feeling of the tusk, cried, "Ho, what have we here? So very round and smooth and sharp? To me 'tis mighty clear, this wonder of an elephant is very like a spear." The third approached the animal, and happening to take the squirming trunk within his hands, thus boldly up and spake, "I see," quoth he, "the elephant is very like a snake." The fourth reached out his eager hand, and felt about the knee, "And what most this wondrous beast is like is mighty plain," quoth he. "'Tis clear enough the elephant is very like a tree." The fifth, who chanced to touch the ear, said, "Even the blindest man can tell that what this resembles most. Deny the fact who can. This marvel of an elephant is very like a fan." The sixth no sooner had begun about the beast to grope, when seizing upon the swinging tail that fell within his scope, "I see," quoth he, "the elephant is very like a rope." And so these men of Hindustan disputed loud and long, each in his own opinion exceeding stiff and strong, though each was partly in the right, and all were in the wrong. So often theologic wars, or I'll say physics wars, the disputants, I ween, rail on in utter ignorance of what each other mean, and prate about an elephant, not one of them has seen. That fits in my mind. So, I want to talk a little bit about the milestones of influence. Obviously, Johannes Kepler had a huge impact on our understanding of the solar system. He's the one that recognized that the planets were in elliptical orbits with the sun at one of the foci of an ellipse, that the sun's radius vector sweeps equal areas in equal times, and the planet's squares of periods are to each other as the cubes of their mean distances. These are mathematical models that turn out to fit the planets. And so he's very famous. That was his contribution, if you will. Well, he's succeeded by Sir Isaac Newton. Mine's one of the greatest men in science ever lived. He laid the basis of celestial mechanics. He's accounted for incredible advances in optics, use of color, and so forth. He's credited with inventing differential and integral calculus. Some people say Leibniz did. They'd added who actually did, but certainly they're incredible people. He was a serious Christian, by the way. He wrote biblical hermeneutics in over 1 million words on Daniel and Revelation and so forth. But what he's really known for, most of all, eclipses these in science. That is, he is responsible for the inverse square law of the theory of universal gravitation. And that's what we're focusing on, because his influence on science and life in general from his universal theory of gravity is profound. But I want you to notice something that's in the official title of that, the inverse square law. That's overlooked by most astronomers. I'll come to that. See, that's the equation of the universal gravitational constant. The gravitational force is a constant times the product of the masses, two objects, divided by the square of the distance between them. Okay? And the g is just a constant depending on what units you're measuring things in. And g, by the way, may be decreasing a little bit. And that's a whole other thing. But the point is really, what everybody overlooks, you have two masses, and you divide by the square of the distance between them. You put them twice as far, they have 1/4 the gravity. You put it 3 times, it's 1/9 the gravity. See, it's the inverse square law. Now, we'll come back to that later. Ben Franklin you don't normally think of him as a man of science, but he made a discovery on June of 1752. He flew his kite with a key attached. And the amazing thing was that he wasn't electrocuted, by the way, but he determined that the sky was inherently electrical in nature. His discovery, really, his realization. No one picked up on it, but it's in the record book, so to speak. Michael Faraday comes along, born about the time Franklin died, by the way, And he discovered what we think of as fields, electromagnetic fields. Albert Einstein kept a photograph of Faraday on his study wall alongside pictures of Sir Isaac Newton and James Clerk Maxwell. So these are the greats, if you will. We'll come to James Clerk Maxwell in a minute. Faraday was highly religious. He was a member of the Christian sect that demanded total faith and commitment. Biographers have noted that a strong sense of unity of God and nature pervaded in Faraday's life and work. I think it's interesting that some of these great minds were God-fearing people. They had different doctrinal perspectives, but they were God-fearing people. Okay, Faraday is followed by a guy by the name James Clerk Maxwell. And he codified all of what we know today of electrical science and engineering into self-consistent equations. And so his impact is not fully appreciated by many, even to this day, and I'll come to that, although he's the foundation for what we call electrical engineering. Electric currents and magnetic fields intrinsically co-occur. They're linked together. Electromagnetic energy propagates through space. He is ranked with Sir Isaac Newton and Albert Einstein for the fundamental nature of his contributions in quantum theory, electromagnetics and electrostatics, thermodynamics, and information theory and cybernetics. And that's the ultimate science, by the way, we'll discover, is information theory itself. Maxwell's equations, you'll hear that term all among engineers, 4 partial differential equations that relate the electric and magnetic fields to their sources, charge density, and current density. These equations can be combined to show that light is a magnetic wave, electromagnetic wave. The interactions of electrostatic and electromagnetic forces are very non-intuitive. I'll show you why a little later as we go here. The forces are orthogonal, that is, the forces are perpendicular to themselves, if you will. Okay? The forces are perpendicular to the fields involved. The resulting plasma, we're going to discover, takes on a unique aspect as a composite body, a very distinctive character. That'll be clear as we get into that here in a minute. Individually, these equations are known as the Gauss's law for magnetism, Faraday's law of induction, and Ampere's law of Maxwell's correction. These 4 equations, along with the Lorentz force law, complete the set of laws of classical electromagnetism. Fabulous though these are, what's astonishing we're going to discover is the astronomers have tended to ignore this to their detriment. Well, along comes a guy by the name of William Thomson, who gets knighted as Lord William Thomson, Lord Kelvin they call him, and he's one of the most influential scientists in 1900 Great Britain. Okay? He was knighted for his work in thermodynamics, but he was a very outspoken critic and pessimistic about the future of electricity and electromagnetic theory. He felt that radio and wireless telegraphy had no future. Now, he's a very, very influential man, but he took a position against electromagnetism. And as a result, the whole British scientific establishment tended to go down a path of ignoring Maxwell. Okay? He'll be rediscovered later, but the point is, he is thus, while he's very influential in very positive ways, he's negative in terms of his impact here. Okay? So I want to pause here and talk about a model not of our solar system, let's put it this, the solar system is the sun and all the 9 planets, okay? Let's make a model. There is a celestial publication, almanac, in which Burnham notices something interesting. The number of inches in a mile happened to be 63,360. Just happens, that's how many, in a mile, that's how many inches there are. In astronomy, the distance between the sun and the earth is considered a basic astronomical unit. They use that as a unit of measure. Well, it turns out a light year is how far a light can travel in a year. That's another measure. The number of astronomical units in a light year happen to be roughly the same number of inches that there are in a statute mile. That suggests then an interesting scale to use. If you're going to build a model of the galaxy, why not use the inches, let an inch represent an astronomical unit, and build your model. You follow me? To get a feeling for these distances, okay? Well, the astronomical distance from the sun to the earth is an astronomical unit, as I've mentioned. Now, in Burnham's model, 1 inch represents the distance from the sun to the earth, right? Okay, so we start, and of course 1 mile represents a light year. So we start to build our model, we need to make a place to start, the sun. The sun's about 880,000 miles in diameter. It's about 90. If I'm going to take that part of 93 million miles that the sun is from the Earth, I've got to make the sun 0.009 of an inch. Now, make a dot with a very sharpened pencil, like a period. That's going to represent our sun. 1 inch away, we put the Earth. You with me so far? Okay? So let's call it 1/100th of an inch diameter is a tiny speck. And all the planets will turn out to be within a 7-foot circle. Mercury will be about 4/10ths of an inch away from the sun. Venus about 7/10ths of an inch. Earth 1 inch by definition, right? Mars about almost twice that, 1.6 inches. Jupiter about 5.2 inches. Saturn 9.5 inches. Uranus about 19.2 inches. Neptune 30 inches. And then Pluto 39.5, almost a meter, call it. Okay, so it turns out if we were building this model, we could put the whole thing inside of a 7-foot circle, right? You with me so far? Okay. Now we want to put the nearest star. Well, the nearest star is 4.5 light years away. Okay, so we have to put that star 4.5 miles away. Get the picture. The Earth and the sun is 1 inch. The next star is 4.5 miles away. Do you get a feeling for the sizes here? Okay. 2 specks of dust 4.5 miles apart. How much gravity do you think would have an impact there? The distance between them is squared and divided into it. In other words, it's de minimis. De minimis. If we visualized the sun as a golf ball, the next star would be 700 miles away. If I've got 2 golf balls separated by 700 miles, how much gravity do you think they feel with each other? None, of course not. So, if we made this model further, our Milky Way galaxy would be 100,000 miles in diameter. Now let's back up a little bit and refresh some things we learned from some of the earlier sessions here. If we have a model of the atom, we went through this before, you got a nucleus and an electron. This is not to scale, obviously. We know nucleus is in the neighborhood of 10 to the minus 13 centimeters. The atom itself is about 10 to the minus 8. The ratio of that is about 10 to the 5th. If the nucleus was 1 inch, there's 100,000 inches in the orbit. 10 to the 5th. 100,000 difference, okay? But that's linearly. If I want to look how much area does that, we have to square that, right? It's square. If we're making a 3-dimensional model, a 2-dimensional model, we've got to square that, okay? And if you want to get the volume, you've got to cube it, right? Length, width, height, right? So you take 10 to the 5th and cube it, you've got 10 to the 15th. That's a big number. 10 to the 5th to the cube is 10 to the 15th. How much is that? That's a ratio, the same ratio that 1 second would have to 30 million years. So if I have an atom anywhere, and I say there's nothing there, and you insist there's something there, I'm more right than you are as 1 inch. I mean, the physics of it would be the physical part of it is same ratio as 1 second would be to 30 million years. In other words, this podium is mostly empty space. The part that's not empty space is the same part that as 1 second would be to 30 million years. Why does it feel solid? Because it's an electrical simulation. The electrons of the atoms that make up this podium are colliding with the electrons that make up the molecules in my hand. That makes it feel like it's solid because they are colliding in a predictable way. But is there really is there something solid there? No, it's mostly empty. Hard to get used to, but it's important to see where we're going. We touched all of this on beyond perception, and as these various nuclei share electrons, you start making atoms become molecules, and those molecules become other things. So, if we start with a lot of nuclei and a lot of electrons, that's called a plasma. And so I'm using oxygen here as a blue dot and hydrogen here as a yellow dot. If I have a whole bunch of oxygen atoms, and they capture electrons that are free electrons. When it's in the plasma state, they are flowing as pieces. But as they start to get associated with each other, they become a gas. And the gas, as you start cooling it down, from gas down, you finally get a liquid. It gets into, the liquid. And like propane, we have propane, you get liquid. And then finally you get down to a solid. Okay. If you heat the solid, it becomes a liquid. You heat the liquid, it becomes a gas. When you heat the gas, it can become a plasma. The big thing is don't confuse plasma with gases, okay? Because plasma has a whole different behavior. We've got a little model up here that you can take a look at where you can see the behavior of arc. Plasma has three modes. We're going to get into that in a minute, in the next session actually, where the plasma has, where you have it's dark. Other conditions it will be glowing, and then it's got a third mode called arc mode, where it actually is like lightning or like a welding torch and so forth, and or like what goes inside in a fluorescent light, similar kind of thing. The nature of matter. Now, as you go from, you have four states of matter, not three. Most of it are solid, liquid, and gas. No, there's a fourth that we all overlook. Plasma is the most random, solid the most orderly, most structured. Everything else is measurably between those. It's interesting that while the British were disparaging electromagnetism, the people up in the Scandinavian countries, in Norway and Sweden, their scientists were fascinated with the auroras. And they quickly realized that the auroras are electrical. And so they really got into plasma physics. The founders of plasma physics, in large measure, were the very northern latitudes. And this happened to be a surprised one in the southern hemisphere that occurred just a few weeks ago when I was down in New Zealand. And it was observed from the International Space Station. That's clearly, it's a aurora australis. So we have a plasma universe. The effects of gravity are minuscule. They're not a factor. I'll show you how much in a little bit here. The effects of electromagnetism can be 10 to the 39 times as great. The entire volume of our galaxy is filled with diffuse clouds of magnetized plasma, electrically charged ionized particles. 99% of all matter in the universe is in the form of plasma. Scientists are busily looking for the missing matter. That missing matter is hypothecated to try to preserve their theories. It's not missing. It's there in the form of plasma that they don't recognize. Let's take a look at Andromeda, M31, one of the most famous things in the sky. Beautiful thing. When you look at it in infrared, you begin to realize there's electrical things going on in there. It's not just simple solids. There's significant differences there. M82, if you look at it in different wavelengths, you begin to realize it's an electrical phenomenon. And there it is in the infrared. And it goes on like this. We begin to realize that these celestial objects are much larger than they first appear, and they're connected electrically, not gravitationally. Gravity has nothing to do with it, or little to do with it. These things are electrical phenomena. The more you know about plasma, the more these things can be recreated in the laboratory in smaller size that follow the same laws. And some of these things are really bizarre. You can't explain them with gravity. Here's the star V838 from the Hubble telescope on May 20th of 2002, then September 2nd of 2002, October 28th, 2002, and December 17th, 2002. And it's hard to explain what's going on here by gravity, by the way. See, gravity only attracts, doesn't repel. And there's a lot of other things going on here. Let's talk about our closest neighbor, the sun. When we have an eclipse, we begin to realize there's a corona, and that starts to evidence that it's electrical in nature, not gravitational. And there's a common myth that that's a thermonuclear process going on. Not so. We're going to discover in the next session what it really is, and that may surprise you. Because we begin to see, if we look closely at the corona, we begin to see things that are happening that are not gravity at all. And this is a picture of the corona. We're going to talk more about the next session. But I got a movie I'm going to try to show you. As you watch these corona flares and so forth, it's obvious as you watch them they're following magnetic paths, electrical paths. They're behaving according to a set of laws which are understood, and from that behavior, we don't have all the answers to all the questions, obviously, but it's amazing how much of what we didn't understand about the sun suddenly does make sense. Well, this series is the fourth in a series called The Boundaries of Reality. And I'm using the Vitruvian man as a symbol of man's reach, as I have before, and the other things. Size is increasing to the right here. And in our early things, we talked about the macrocosm, of course, which is finite. That gets us into astronomy and astrophysics and all that. We then went into the quantum physics, the microcosm, smallness. And as we explored that, we discovered the universe is made of indivisible units, basic units that can't be divided. That's the field of quantum physics and subatomic particles. And the metacosm that this is all in then, putting this all together, is we discover is actually a digital simulation. Because on the large side it's finite and quantified, and on the small it's quantified. It's always made of indivisible units. Now, in an article on this subject in the Scientific American, they point out that if these units are changing their size, then that implies that our reality is but a shadow of a larger reality. So far we've talked about the big side, the macrocosm, and microcosm. We now have gotten into we're going to get into next session zero-point energy, which will lead us into plasmas, and we have closed the loop, if you will, of this entire program. And so that's our next session.